Okay, thanks for the kind introduction, and it's a pleasure to be here in this amazing conference. So, I am Emanuele Calabró from Halocell. I'm a materials and device scientist, and we'll speak about peculiar perovskites. So, first of all, I want just to mention that recently we changed the name from Gretzel Energy to Halocell. This is why the reason is because we want to stress and highlight that we are moving toward the commercialization on hybrid halide perovskite solar cell. So, why we are so interested in perovskite? This because this material offer many advantages. Is a is a amazing semiconductor that have perfect optoelectronic properties and can be really suitable for all photovoltaics application. The main key points of the hybrid perovskite materials are the high absorption coefficients, the high charge carrier mobility, high diffusion length, an easy solution processability that permits us to have an easy process for large area devices and by using industrial deposition techniques. Finally, the tunable band gap maybe is one of the best properties that we can stress, and I will stress a little bit during my presentation, because by changing some cation or anion in the ABX3 structure, so the A and B, and even the halide sites, we can tune a lot the electronic band gaps, and so we can have the band gap passing from 1.2 to above 3 electron volts. This permits us, if we think about the different illumination spectrum as represented here on the left, that we can have many opportunities in the application. In fact, if we see the broad spectrum from the solar sun, so for the sun, so the IM 1.5G, you can see that it's covering from the ultraviolet to the infrared. While if we are looking for a standard warm LED light, but if it's cold, it's just changing a little bit the shape with a higher peak close to the ultraviolet, we can see that even with a higher band gap, we can cover all this spectrum. In fact, if we think about the maximum theoretical efficiency that we can get under one sun, everyone knows that the short frequency limit has a limit of 33% for band gaps close to 1.1 to 1.4. Instead, if we check the green line that is referred to a warm LED, we can even achieve how much higher performances under indoor light. So this permits to that the artificial light can be efficiently converted into electricity. In the last decades, we everyone saw that there is a huge increase of terms of Internet of Things devices or low power management devices. On the left, we can see a graph that is showing how is now the incoming of for the wireless sensor, for example, in the last decade, and is now is more overcoming the 10 billions of USA dollars. And in parallel, we can see even that the indoor photovoltaics market is increasing a lot. This is why, because on the right we can see is a graph where is represented the average power consumption of some of the low power application like air feed, LoRa scattered, passive Wi-Fi, and we can see that all of them has a power consumption lower than 1 millivolt. So it means that if we have very high efficiency photovoltaics that can work well under indoor light illumination, just few centimeters square of active area can be sufficient to power them. It should be amazing even if it's flexible, if we can have a flexible model, so we can permit to have high power per weight efficiency and even an easy integration into device Internet of the device surface or close to them. So this is our roadmap from Halocell that we are developing in those years, because now we are in the horizon one, so close to the indoor devices. We have dozen of customers that are already interested in our product, because we can tune, customize the shapes of our solutions. Of course, in the future, we will go close to outdoor devices, pushing to different application, so like full sun, build integration, automotive, and to